At the bottom of the Mariana Trench, the ocean pushes with roughly 16,000 pounds on every square inch. A conventional naval submarine is not designed for this pressure. Once its collapse pressure was exceeded, unstable buckling could occur in a fraction of a second. Yet, purpose-built vehicles have reached the bottom and returned. So what separates a surviving pressure sphere from a crushed submarine? At the surface, a submarine hull only resists a small pressure difference. But every 10 meters of descent adds roughly another atmosphere of water pressure. At Challenger Deep, almost 11 kilometers below the Pacific, pressure reaches about 1,100 atmospheres. That is close to 16,000 pounds of force on every square inch of the pressure boundary. On just 1 square inch, that is roughly 7 tons force. And the load is not applied in one direction. It presses inward from every side, continuously. The outer shape we recognize as a submarine is not always the part keeping the crew alive. Inside it sits the pressure hull, the sealed structure that must remain stable while the ocean tries to collapse it. Long cylinders provide room for machinery, batteries, propulsion, and a working crew. Rounded ends reduce stress concentrations, while internal frames help the shell keep its shape. External pressure creates a dangerous failure mode, buckling. A tiny imperfection, weld distortion, or local change in thickness can concentrate stress. A cylinder has no curvature along its axis, which makes it more vulnerable to external pressure buckling. Once part of the shell moves inward, it starts losing the geometry that carried the load. Failure can then accelerate faster than anyone could react. The exact operating and collapse depths of military submarines are generally not public. It would also be misleading to name one universal crush depth. Material, diameter, wall thickness, stiffening, fabrication, and damage all change the physical collapse limit. Safety factors instead set the permitted operating and test depths. What is clear is that an ordinary operational submarine is not built for 11 kilometers. Full ocean depth vehicles solve a completely different problem. Instead of carrying a large crew for months, they protect a very small crew for a specialized dive. A long cylinder is space efficient, but a compact sphere is stronger against uniform external pressure. That mission trade changes almost every engineering decision. A sphere's continuous double curvature distributes compressive stress around the shell more evenly. Unlike a cylinder, it has no uncurved axial direction that is especially vulnerable to buckling. The geometry is less convenient inside, but far better suited to extreme pressure. The sphere still has to be extremely thick, precisely manufactured, and carefully inspected. Every viewport, cable, and hatch interrupts the load path. The vehicle also needs buoyancy material that does not crush and reliable ballast release. Electronics may be pressure-tolerant, oil-filled and pressure-compensated, or enclosed inside pressure housings. If normal power fails, dropping ballast must still bring the vehicle back toward the surface. In 1960, Trist carried Jack Pickard and Don Walsh to Challenger Deep. Decades later, James Cameron made a solo descent. The two-person limiting factor then completed repeated full ocean depth dives. These machines did not prove that any submarine can survive the trench. They proved that a vehicle designed around pressure survival can. So, could a modern submarine survive the Mariana Trench? A conventional operational submarine, no. Long before the bottom, external pressure would exceed its design envelope and buckling would become catastrophic. A certified full ocean depth submersible with a thick pressure sphere, yes. Nearly every part of it is designed around that one extreme. At 11 kilometers down, power and speed are not the decisive advantages. Geometry sets the terms.